那是庞克头，胖季剪的没？是季剪的没？那个头发是自己剪的没？去外面剪？不是去外面剪啊。
因为你那时候不是自己，
我想自己修。
然后修了一条线，
真的没？哪里有一条线？后面
断层。
哦。变慢一点，缺一点。好，没有 Pro 今天。我们要不要再等人，还是要开始？啊？下一层呢？帕头，我不知道是真帕头还是假帕头。
转引起冲二口。
Anyway，有享受到就好。不贵，真的不贵啊。
都可以活几千年。
它
这个是还是幼崽？
它放在哪里？
包里面。
哦，杯里面。
然后放在桌子，好，还帮它捞大便哦。
他太紧张了。哦。
看说他的屁股，那个大便从他屁股出来。公公，那他会是到上次我们。
我们要不要等摇一层？
等他，然后他来我讲我们来等。
那我们就讲 class cancel。好啊，上个周末啊，怎样？你好，终于来了，终于来了啊！迟到了，不是迟到哈。对呀。
对不起，我错了。
Okay, today class cancel. 啊，class cancel. Okay. Today we're not gonna do too many proof because I don't have internet. I was underpaid, so the proof is also underprepared. So reality is we will go through two dimension, and then there are a lot of commutative algebra result. Maybe I will add it into the notes or add it to the tutorial sheets. And then we will do glow up. There's some part that I haven't fully understand yet. So maybe we will just look at some statement first, and then hopefully I can figure out this week, and then we can continue with revise the next week. Okay. Okay. Yeah. I was busy with a lot of things. Thank you. Okay, so in that case, let's talk about Krull dimension first. So this is the part where we will link the algebraic dimension with dimension of variety or dimension of topological space. Okay, so in this topic, right, since every variety is birationally equivalent to an affine projective set, so we just consider all V as affine variety, because yesterday we showed that if two variety are birationally equivalent, their dimension should be the same. Okay, their dimension should be the same, so we just look at affine variety. And yeah, and then we defined this. So let's define this. So V is a Noetherian topological space if every descending chain, let's say V equals to V naught, P1, V2, so on, VL, okay, of irreducible closed set has finitely. Have we introduced this terminology before? Have we introduced this terminology before in this class? Not, we did what? Noetherian ring, Noetherian module. Okay, maybe we haven't introduced this word, but this idea you should have seen before, right? What kind of space is Noetherian topological space? I think you saw this kind of chain before, right? But the chain should be in ascending, right? Ascending chain condition. When do you have ascending chain condition? Z mod. What's Z mod? Z mod n. Noetherian ring. Mod thing. Z mod 12 Z, huh? Is Z mod 12 Z a Noetherian ring or not? Is it? Is it Noetherian ring? Z mod 12 Z. Hmm. Yeah, but you need to show for every, right? Every. You just write down one. Need every. Is it principal ideal domain? We show that principal ideal domain is Noetherian, right? Huh? What kind of space is Noetherian? What's the only topological space you see in this class? Zariski topology, right? Okay, so varieties in particular is a Noetherian topological space, because if you look at the ideal, is it? You look at the ideal. Yeah, you look at the ideal that define this V here should be Noetherian, right? Okay. Okay. So in this case, what we're gonna define is the Krull dimension. Okay, so the Krull dimension of a topological space V, which we written as KR dim V, okay, is the supremum, yes, sup of the length of all
descending chain of irreducible closed set. Okay, you look at the largest length of all descending chain. Okay, and then in this case, we'll define something on ring now. Okay, and then try and relate the two dimension. So first, we'll define what is called the height. Okay, so height, this is height defined on a prime ideal. Okay, so prime ideal, what's the height then? Height will be the supremum over the length L of all chain of prime ideal. Hey, by the way, yesterday, right? Yesterday's some of you went to the talk, right? When you went to the talk, let me tell you something extra here. You went for the talk, you see some spec, right? Spec of something. Did you see spec yesterday? Actually, this is just a set of prime ideal of A, that's all. We call it a spectrum. So it's a spec. Okay, yeah. Yeah. So if we go further in algebraic geometry, really we are just interested in the prime ideals. And then prime ideals has a bijection with points in the ideal defined on A. Okay, so chain of prime ideal of the form. So in this case, we will have an ascending chain here. So, okay, and then we will define what's a Krull dimension for a ring also. Okay, just now we define Krull dimension for topological space. Now we define Krull dimension for ring. Okay, so we will denote that as dim A. Okay, we didn't write Krull A here. We write dim A. Yesterday we defined dimension on variety, right? Okay, so that one is defined using the minimum of dimension of a tangent space. Okay, if your affine projective set is not reducible, then you look at the maximum of these minimum. Okay. Okay, so Krull dimension of A, we write it as dim A, is the supremum as well. Where over over the height HTI of all prime ID. Okay. Okay, so what do you expect here? So there are true dimension for A, true dimension for V. Okay, how do you relate these two? If I give you a affine variety, can you cook out a ring or not? The coordinate ring. Okay. So if you have a chain of irreducible closed set here, meaning what? These are the zero set of some ideal. So if you have inclusion, okay, on one way on the closed set, then it will induce a inclusion reversal property on the ideal defining this variety here, this closed set, right? Make sense? Okay, so if the descending chain of a variety terminate, obviously the ascending chain of ideal also terminate. Okay, so these two supremum actually refer to the same chain here. I mean in bijection. Okay, so Krull dimension of V actually equals to the dimension of V. Okay. This just refer to this implication here. So if you have V0 containing V1 containing V2 and so on, then this will correspond to an inclusion reversal ideal containment. Okay, make sense? Okay. Okay. Next part, I got not gonna to prove. So next theorem is let A be an integral domain. Which is also a finitely generated K algebra. There's a mysterious condition in this theorem. I don't know where to use it, but I can write it for you first. It's appearing in the clause notes. Let K be a field of fraction of A. I haven't dig out the proof yet, so maybe after I dig out the proof, maybe I know what happened. But the result is nothing about this field of fraction. Then dim A equals to the transcendental degree K over K of A. I don't know where they use the capital K at the moment. So yeah, but basically it's the Krull dimension of A is equal to the transcendental degree of A. I'll dig out the proof later, but yeah. Yes. This little K what? Unique? I mean unique. It is fixed. You mean it is fixed or not?
I think the internet chat technically works.
Well, I mean like A is a finitely generated K algebra, so K is fixed here. So what's the problem? You mean oh okay, so you mean let's say it is finitely generated with different K. Does the transcendental degree changes or not? A priori, I think it could happen. So let me see. Ideal. Okay, ideal doesn't have anything to do with. Okay. Let me think, huh? Can you simply change K or not? Think. If A is an integral domain, A, which is finitely generated, have we proved something on this kind of ring before? So we prove that A is a integral domain and algebraic, then A is a field. Okay, I think this is not what we want. If A is a field and contain, we're not sure whether A is a field or not. Okay, never mind. So we want to combine integral domain and finite generator together. You know, A is a field. Okay, never mind. Yeah, I think maybe we can try and think about this. Yeah, does this K matter or not? Because I haven't solved this mystery yet. Maybe there's something to do with this field of fraction. But field of fraction surely contain A, right? It doesn't make sense to say A over this K. I'll try and find it out later. Yeah. So
So the train stopped at you cannot just the phone. I don't want to have any relation.
wait, so why you trying to argue here?
I'm trying to argue maybe
Independent of K. So you mean maybe there's some field in between A, something like that. I mean, it could happen, but I mean, I'm not sure how it will affect. Will be the case that it finally generated over K, but not over this middle field here. But no, huh? Yeah. But I mean, like for Noether, can we use Noether normalization theorem here? I think we can, right? Finally generated K algebra. So you could find something in the middle, right? You can find something that are not algebraically dependent and then make it a field. Yeah, I'll try and figure out this. Hey, yesterday problem, anyone figure out already? Yesterday we also got problem, right? Anyone figure out the problem yet? This problem. Anyone figure out? Not yet. Huh? No. Not yet. Anyone figure out this yet? Try and think about it before I give you answer. I think we need it today actually. Okay. So so a corollary is if V is an affine variety, then through dimension, okay, counting the ascending chain, okay, descending chain, okay, is actually equal to counting the minimum of your dimension of your tangent space. Okay, both of them will pass through the transcendental degree, okay, of KV. Okay, the right hand side is what we have proven yesterday. Okay, so today then we will make the formal connection here. Okay, so just now, so this proof here, I'm not sure got bug or not. Let's see it. So through dimension V here, just now we show that it's equals to the dimension of KV just by the ascending chain, descending chain bijection. Then from the definition just now, right? This is equal, this is this is integral domain, right? Because it's irreducible. Finally generated K algebra, okay, because it's Noetherian. Then this is equals to the transcendental degree of KV, okay? But I would like to say that this is also the transcendental degree of KV, the fraction field of KV. Then this is equal to dV. Is the third equality works or not? Okay or not? I haven't quite write it down yet, but I think we somehow need to pass to this stage. I don't know whether that theorem got a problem or not just now. Yeah. But you mean from here to here?
Yes.
Oh.
Using the that just now the definitional dimension.
Which dimension? This dimension. Times dv.
Yeah.
This is a minimum of tangent plane. True dimension is the. And this is a so okay. So let me write down. So this part is the topological dimension. On the Noetherian one, topological, and then this one is ring, right? Algebraic. So and then transcendental degree, and then the bottom one is on tangent space for variety. What do you mean?
Dimension should be the dimension right should be same as the dimension of dimension of the topological space.
Yeah, we are showing now. We are proving it now. This is what this theorem tries to show.
Those are shown the exact definition.
Yeah, so we are proving it now. So we pass by this algebraic dimension here. Well, I think, yeah. What do you think? Maybe you think it's obvious. Okay, let me know. You don't think it's obvious? You don't think? You don't think it's obvious? I think if we solve the yesterday problem, then this will be obvious. Huh? Why? So okay, so what's the transcendental degree here? It just asks you whether what elements are algebraically independent with each other. How many of them? If the number of algebraically independent elements, both of these are the same, then the number is the, I mean, this degree is the same. This is a bit like, you remember the question I did in the tutorial? If AI to AN are algebraic, the polynomial ring adjoint this AI, right, is actually the function field. Yeah, it's actually the field of fraction. If all of them are algebraic. Tutorial, yeah. You have an idea.
B is actually field of fraction of the number.
Yeah.
And in that field, we only have an inverse.
Yeah.
But all inverse we can express it as something x minus 1
X. Yeah, sure, yeah, sure.
So when we put it not as that, because it is a solution of a polynomial.
Then.
So we did not add more transcendental.
Oh yeah, sure. Oh, I get what you mean. Oh, I get what you mean.
the transcendental degree of K 方括号 B to K 圆括号 B is 0.
But I mean like square bracket and round bracket. So do you mean true that this is just this? How would you write down? Adjoin all the inverses. Is this true? Do you adjoin more inverses or not? How many things you invert here? Wait, let me see. Yeah, everything is not inverted. Yeah.
But that's not coefficient lives in a square bracket. So
Yeah.
the things that we had is not transcendental algebraic.
True. True.
Yeah.
Yeah, I think makes sense.
So this thing should be
Okay. Okay, I think sure worth to write it down. Try and write this argument down here. Okay. Anyone get what Eric said? Does anyone get at what Eric said? Huh? Anyone get what he said? No. So I mean like what's the difference between K bracket V and K square bracket V? In the function field, all the elements should be invertible, right? But how do you think about inverses? How do you think about inverses? Huh? Sorry? Uh, not about regular, not irregular, just inverse, normal inverse. Normal inverse, what does the normal inverse property? That one is about function. Inverse. Group theory. Inverse. In group theory, what's inverse? Something that you multiply to x, you get 1. So how to add inverse into a ring? Huh? How to add inverse into a ring? Huh? I mean using quotient. How to add inverse into your ring? Do you know this? What's this isomorphism? What's this isomorphism here?
show that the L is y minus y.
Yeah, that's it.
So how do you add an inverse? You just adjoin an element and then quotient like the inverse relation. And that this map is surjective with this term. And then he say you just adjoin a bunch of things and then you quotient up by a bunch of algebraic relation here.
So you are not adding algebraically independent element into it. And this is what he claimed. Kind of makes sense, but try to write the full argument now. Yeah. I can follow Adrian. Huh? Which part cannot? Going to sleep. Okay, I cannot help. Okay. Okay, any question? Any question? Question? Any question? No. Okay. Makes sense. Makes sense. Okay, try and write it out. Okay, try and write the argument. Okay. Next part. Also don't have proof yet, but maybe worth to tell you. So if we have alpha variety, let's call it V. Okay. Then at every point, actually, if you compute the dimension of your local ring, okay, it is actually equals to the dimension of the coordinate ring. Okay, if you are R5 variety. Okay, kind of strong. And then next is about commutative algebra proposition. So if you are Noetherian local ring, okay, so meaning you are local ring and you are Noetherian. Local ring means what? Means that you have a unique maximum ideal. Okay, so let's call it M. If you look at the residue class field here, so meaning some residue field, so meaning you just take your A quotient out by M here, you'll get a field because you are quotienting out by maximum ideal. Then the dimension of M over M squared here, okay, is greater than or equal to dimension of A. Okay. Yesterday, what we have established was the tangent space, okay, is isomorphic to the dual of MP over MP squared, okay, the maximum ideal at P. Then we call this MP over MP squared dual as a Zariski tangent space, okay? We call it as a Zariski tangent space. And equivalently, we can call MP over MP squared as a Zariski cotangent plane space, yeah, okay? So the relation about tangent and cotangent is cotangent is a dual of tangent, okay? Right, and then we want to deduce something on our surface here. Okay, so this is a random ring property, just some maximum ideal. Okay, now we're going to draw some corollary on our variety. So let's say we'll call a Noetherian ring A, okay, with maximum ideal M, a regular local ring. Okay, we'll call a local ring regular. Okay, if the above inequality become an equality. Okay, if the above inequality here become equality, we'll call it regular. Okay, so corollary is a point is smooth if and only if the local ring here is regular. Okay, so how do we prove this? So let's quickly write down this proof here. So when is a point smooth? When is a point smooth? By definition. When is a point smooth? that exists what? That one is just hypersurface, right? How about general affine variety? Hypersurface, you need existence of any partial derivative, non-zero partial derivative, right? How do you generalize to affine variety? What's this condition? So how do we generalize the smooth property on smooth point on hypersurface to smooth point in a variety? dim TPV equals to dim V. Okay, dim TPV equals to dim V. Okay, so dim TPV equals to dim V means what? The dimension of your tangent space have to be the same as the dimension of your variety. Okay, then you are smooth. Okay, imagine something is not smooth. What happened? You just think about hypersurface case. There doesn't exist a non-zero derivative, right? So the partial derivative equation that you get is zero, right? Then what are the zero set of a zero polynomial? The whole space. Okay, but let's say you define a hypersurface on degree 2, dimension 2. Okay, then the whole space is dimension 2. But what is the dimension of a hypersurface? N minus 1. So 2 minus 1 is 1. So at the singularity point, right, always you will have larger dimension. Okay. So in this case here, together what we have established was so dim of m over m square here, okay, should be equals to dim v. Okay, but we know that dim v actually is the same as a topological dimension. We call it Krull dimension. But Krull dimension is equal to the dimension of coordinate ring, okay, using prime ideal. But just now we didn't prove, what we didn't prove was this dimension of KV is always equals to the dimension of the ring. Okay. Make sense? Okay, so first part is smooth. What do you mean?
Maybe I forget what it.
You mean this? Oh, this is a vector space, I guess. Let me think. This should be a vector space, yeah. Yeah, I guess. Yeah. Because tangent space is a vector space. Yeah. Yeah. So this is a vector space dimension, then this is a variety dimension. Because the variety dimension defined using vector space. Okay. And then Krull dimension is a topological dimension. And then the dimension of KV is the algebraic dimension of ring. And then dimension of OVP is the same, right? It's the same dimension. Same kind of dimension. Okay? Is it fun? Not fun. Yeah, you must feel fun so you can do research. If not fun, then you cannot do research. Yeah. If you think that this level of maths you already enough, then enough for you. You cannot continue anymore because it's harmful for your health also. Yeah. But if it is I mean, if you are happy but it is harmful, then you actually can revert this effect. Yeah. You know, got some people they got cancer, they don't die actually. But some people they got cancer, they die pretty quickly. What's the difference eh? You know what's the difference or not? Huh? Sorry? Some of them is same kind of cancer, you know. Huh? Yeah, if they are happy. I mean, if their attitude. Okay, this is just about attitude. Everything is just about attitude. Yeah. Yeah. It's just about attitude. Yeah. Should I talk about my relative? Should I? I got a story actually. I got two relatives got cancer. Okay, after this we can take a break from it. I got two relatives get cancer. Lah. Both are my auntie, but from different side. I think one is older than the other. Which one you think die first? Okay, 不是诅咒啊 no how to say curse here, not cursing. We are just discussing. Maybe from your view of point, from the information I give you, who should die first? Or maybe you say information insufficient. I also can accept. I didn't tell you much yet. So the reality is one of them already died. Actually, both of them, the last time I saw them, right, they are pretty bad. Pretty bad. Pretty bad means what 啊？就是那种死样。我不是骂他，就是 like almost dead, like very weak 啊 yeah, very weak. One auntie, I didn't see her for long already. Then my mom every day call me. Then one day he told me, he went to our house. I'm not at home. I was in SMUM. Then my mom told me, hey, your auntie look better already now. Look better already. Kind of recovering. The other auntie, one day my mom called me. Hey, just now afternoon, I want to call you. Why you not pick up? Ma, I'm teaching. Then he told me, the auntie died already. I guess it's their attitude towards life. When I go back Chinese New Year, I met the auntie who already died. She's so weak already. She's so weak. Very weak already. Still, the mindset is still very negative. Very negative. How negative is it? Cannot appreciate what people do for her. She's already so weak. People have to like walk her around. But her mindset is still negative. How negative? Cannot appreciate what people do for her. Just like to complain. I'm not scoring any one of you. But now you are healthy, I tell you. If you are not healthy one day, you will die quicker. So sometimes I don't want to comment about your lecturer, your teacher. But they already get so old. They still have this negative mindset. Who can like take care of them? Who dare to take care of them? Hey, my grandma is like that. None of the daughter-in-law dare to like stay for long with her. You know what is daughter-in-law? 媳妇. Or is his son one? My father lah. His son lah, sit at the side lah, half day change shift. She also negative. Well, yeah, very negative actually. I mean, she's relative better with us lah. Us meaning, we are like a grandson or grandchildren that not always live beside her, so she will talk nicely. But for those who like always stay with her, very back check her one. Because her comment is not somebody can withstand one. Sometimes, maybe for most of the time. So I mean, there are few ways to die lah. I think either you want to die happily or you want to die sadly. That's it. If you choose to bring this negativity with you, you don't want to listen to what people tell you, and people is not like how to say hating you. I think you try and listen different view, even though you don't want to accept. I think it will be better for you. Yeah. Okay. Attitude is pretty important. Some facts you cannot change, but what can change is your attitude. That's it. It's serious, huh? It's really serious, huh? Maybe now you are still healthy, still young, what? When you get to the age, then you will realize. I haven't get to the age, but I observe. I observe. Okay. Because I'm a scholar. I observe. Okay. Okay, let's break until 5:02.哎，子谦呢？是啊。哎，你们这个办事还要 meet 吗？还是你们 OK 啊？就这些吧。这个东西问啊？这些。对哈。但就不要变。我要开始做事情了，很多事情我没做。
没有，你在那个讲啊，看到谁要一个
对，看这样。
他一点，
我每个星期花了
是吧？最后不有机会这一点
5个小时，对不对？5个小时啊，我就做每个星期，就等于。啊？啊？怎么样？会没有那么喜欢？
没上去，一个半的没到。
所以这个最出题目就是
对，要最平常。
介绍
真的要对平常。我今天发现到这个题，我发现我数学因为我做不出来，就某个怕我希望它是对的。你最近一直想不出，所以后来发现那个东西其实没有读出来。我觉得我是从你读书发现到那么差。
是自己想要替代
对，对，你要自己在你的节奏中进步。
到现在都是这样。第一个是
做研究会有这样
还有对啊，想做而且不好，也慢慢，可以而且要社区什么？不是的，是吧？对啊，我的天啊，这个大呀！对啊，白做工，我觉得。我们不要再这样，FIB 不要再这样，你不要再这样。
为什么这两天感触那么深？
你们打压我啊，怎么敢做不成啊？
小小猫
啊？
这种猫，
你说我吗？你没有说我们，
我们
要做
打压其他事情，肯定打压他的主语肯定不是我们。谁打压你？谁打压
你也是要分，然后。就是你要这个什么？就把他们在这个。
哎，你刚刚那个
什么？他少给我钱，你们 proof 就少看一点了。
啊
慢讲，慢讲，
？Alright，
本来就这样了，不是？你还我100块，我不是 proof 100%给你吗？
哎，学
你还我
校
80%，我不是 proof 80%就好了，
所以学校在我们身上压榨，然后又在你们身上压榨，
对不对？所以钱跑哪里去？
钱跑到哪里去？
钱跑哪里去？
所以他们还需
我要去报警啊！现在，我觉得有，
对啊，他在那个招生简章里面还写了。
因为他是下
我觉得有刑事案发生。
哦，
所以说下学期来的新生，
他在那边写汇率是1.64，真是抢钱呢。
他拿一个年里的最低的汇率。
对啊，学校太恶心。
这个可以报警的吗？
可以
想报警啊？啊，
是
然后我去想报警。
不要
是这样子的，
你那中文清楚。
嗯，是这样啊。
也
对了，
当我这件事，反翻正
反了，画
哦，
反了。
对
Cytomorphism theory 不是这么用的。
哎，反了，那一反啊？
这边送到这边，
哦，对，啊，这里去，这里去，
要 subject to matter 这样子。
这样吧，
对，这样的话是对的，因为你是脱选的是这个东西，脱选
是那个 Y 是
我记得 Larry 在 seminar 的时候有 proof， 等于全色再加上全色 AB，
transitive
全色等
transitive
对
OK
Larry proof 过这个，所以我刚刚说的其实就是 transcendental degree of K 方括号 V K 圆括号 B 是0。
啊？
这问有问题。
就我刚刚跟你说的东西，其实是 transcendental degree of K 方括号 V， 然后 K 圆括号 V 是等于0。所以说那个 transcendental K K V 等于 transcendental K K V。
别像那三个东西出来。
加就是 transcendental degree of AB 等于 transcendental degree of AC 加上 transcendental degree of CB。这个 Larry 在下面的时候有 proof 过，我们可以到时候去 call 一下当时的 proof。那么 transcendental degree of K， 然后 K 圆括号 B 就会等于 transcendental degree of K 方括号 V 再加上 transcendental degree of K 方括号 V， 然后 K 圆括号 B， 然后我们看这个东西等于0，所以这个等于这个。OK，
Y
什么？
摸个等于零。
这个等于0就是因为我说你从这个东西扩展到这个东西，我刚刚在 claim 的是你加进去的东西全部都是 algebraic 的，不是 algebraic 的，不是 transcendental 的。
Algebraic in what sense 是 dependent 的。
algebraic 的意思就是它是那个 ring 里面 coefficient 的一个 polynomial 的 solution。因为显然你加进去的所有东西其实都是这个 k 圆括号 v 的 inverse， 对不对？
对。
那么你就可以把它表示成是 solution of 这个东西，对不对？
对哦，所以
所以你加进去的东西都是 algebraic 的，不是 transcendental 的。 这种那个。
但是我们不是加 polynomial 进去吗？我们加 inverse 是什么？
加的 polynomial 就 polynomial dependent 了。我们在讨论的是没有 polynomial dependent 的东西。有 polynomial dependent 的东西不会增加 transcendental 的 degree。
因为它的 inverse 一定会符合这个条件。
对啊，
因为你 quotient by 这
还有一个 polynomial degree，你可以把它想成是 quotient by 那个。
所以我的 quotient 掉了，肯定是没有关系的。
啊？没有，就是来它有一个 polynomial 的 relation。昊天呢？昊天没有在啊？不知道。
干嘛？
慢么？
做 spy。
它是什么 spy？
我还没有听到。
Okay, so prepare for the resolution of singularity, right? Let's start. Okay, to prepare for the resolution of singularity, we will talk about tangent cone first. Okay, so what's a tangent cone of an affine variety? Later I'll draw some picture for you. Maybe it will be more catchy there. So what's a cone? Last time we defined an affine cone, right? What's an affine cone? Basically, you take a zero set of projective algebraic set. No, zero set of a homogeneous ideal, which is a projective algebraic set, and then you add in the zero. Okay, become a cone. But in general, what's cone? What's cone in general? How do you characterize the general cone? So we'll start with affine algebraic set. Okay, and it's called a cone if for all lambda in K and point in X, okay, we have the scalar live inside X as well. Okay, so meaning X will contain the line through 0 through 0 and P. Okay, so the picture you should think about. Line through 0 and a point P. It must live inside your variety. Okay, if you ever have a point in your variety here, the whole line must live inside there. Okay, so it looks like a cone. Okay, so what's a tangent cone then? So let's define it. So let's take F. Okay, and then let F be written as a sum of Fi, be the decomposition into homogeneous part. Okay, so what's the initial part? So we'll define the initial part F. Which is okay. So how do I put this? Okay, it's defined by F in, okay, which is F, the ith part, okay, the ith homogeneous part for the smallest I such that Fi is non-zero. Okay, the first non-zero homogeneous part we call the initial part because you start there, right? Right, because it's the first non-zero part. Okay, and then we'll say that if you take an ideal, and I will define what is called the initial ideal. Again, the initial ideal. I such that I int is generated by this Fin. Okay. Is it obvious that this is a homogeneous ideal or not? Is it obvious that this is a homogeneous ideal? Homogeneous ideal, what does it mean? Definition. What's an homogeneous ideal? Homogeneous ideal means what? You can write your ideal as a direct sum of intersection between I and the degree D part of the polynomial ring. I intercept as D. Okay. So meaning every element you take it out. Every component of your element should live inside your I. Sorry? Degree D part of the graded ring and I. You get what it means here? So if you get an element out from this homogeneous ideal, okay, then you can write it as a direct sum, right? You split into homogeneous degree. Every term here, okay, or live inside the homogeneous part of graded ring, also at the same time live in I. I intercept as D. Okay, so meaning what? If you have element in I, write it as a sum. Every summand here need to live inside I also. Okay. So the claim here is if you build your initial ideal like this, is a homogeneous ideal. But we prove equivalence statement for homogeneous ideal, right? Your ideal is homogeneous if only if it is generated by homogeneous element. But F in here is homogeneous, right? Okay, because you pick the first smallest degree. Okay. Yeah, okay. So now we're going to define what the tangent cone is. So now let X be an affine algebraic set. Yeah, and then assume we got this 0 point here. Okay, then the tangent cone of X at the 0 point, okay, is what we call the C0X here, okay, at the 0 point, which is defined to be the zero set of initial ideal of X. Okay, so you look at the ideal defining X, and then you look at all the function, and then you chop it. Just take the first non-zero homogeneous part, and then look at the zero set. Then this is called a tangent cone. Maybe at first sight, you might think that, hey, why I want to do this? Later, I can give you some example, right, to see why these things make sense. Maybe you won't prove any result yet. We'll see. Let's see how. Okay. Right. So this is tangent cone. Then you can projectivize it. Okay. You can projectivize it. Well, okay. So if Ix in is homogeneous, right, then this is really a cone. Okay, this is really a cone. And let's see, we want to projectivize it. Okay, so also the projective tangent cone. Okay, how do we projectivize it? What do we mean by projectivize it? Last time, how do we define projectivization? P of some vector space, right? Okay, so can we projectivize this cone here? Oh, okay. If it is a cone, then we can projectivize it. So instead, we'll define CP0 X. Okay, it's defined to be a. Let me think. Can I write it that way? So the boot notation, I'm not sure got problem or no problem. They write like this. I'm still decoding this notation here, but I would like to write in this way. So I feel like I want to write in this way. I haven't really checked it. Huh? I want to projectivize this C0X. I haven't checked yet. I will try and do it before I put out the lecture note. The book notation is this, but I cannot find what is ZH. They have something on IH. So what's IH is the homogeneous ideal. But I don't know what's the homogeneous zero set. I don't think I saw it in the book. Yeah, I posted in your Moodle already. It's by Gotchard. Gotchard is a person where I learn Hilbert scheme stuff. Yeah, well, I mean, so far my understanding is this one. But we'll see. I'll decode it soon. Or you have any idea? No? I actually post the note into your Moodle already. It's on page 40. If not, let me read more first, and then I will update you again. For now, from what I understanding, is just if you have a cone, right? You have a tangent cone just now. Okay. You have this line, and then projective tangent con just means that you view this line as one point. That's it. Makes sense? Huh? Correct or not? What do you mean? Why is it wrong? Yeah, but you can open it up, I guess. You try to open it. You can open it up. Yeah. Sorry? Yeah. So you view the whole line as one point. Just take any point on that line. But not the zero, but not the zero. Do we have zero here? Yeah. But not the zero. Zero is in every line. Yeah, no zero here. Well, okay, this thing I will live in so after projectivize, right? This thing live in Pn minus 1. Right? Because it's originally coming from An, right? So after you projectivize, you go down. Okay. I try to decode what's this. Okay, but this is what I think. Okay. We'll see how. That's why you see me haven't update my lecture now, because there's something I need to fill in. All right. Yeah, I think so far okay or not. Okay, and then next we'll define what is CPX. Basically CPX is just C0 on x minus p. Okay, if everyone happy with x minus p, a variety minus a point, what does it mean? So basically you are like shifting your variety. Okay. Okay, so this is about con here. So shall we see some example? Shall we see some examples here? Let's see some examples. Okay, so for example, I think this is a very nice thing to see. So let's say we look at this conic here. Can anyone know how to draw this conic? Y equals to x squared plus x. How to draw? Someone maybe can get out your Desmos and then try. Y equals to x squared plus x. How to draw this? Maybe you can start from zero set. Huh? Sorry? Oh, okay. If I want to make it equal, then this one becomes minus. Okay, sure. How to draw this? Huh? Sorry? The roots are 0 and 1. Sure. So when y equals 0, you have 2 points, right? How about the other point? Or 0 and 1? Or maybe move here a bit. How about the other point? Do you get? Anyone gets your Desmos? Try help you. Hey, this one is a simple one, right? Y equals to x squared minus x only. So it should be something like this, right? Huh? Okay, this one good. Then what is C0x here? How C0x defined here? So it's the zero set of Ix. Ix in here. But your Ix is generated by what? Generated by one polynomial, right? Okay, so what is the initial part of y minus x squared here? Y minus x squared plus x here. Huh? Y plus x. Y plus x. Yeah, y plus x. So y here, right? Y minus x. Y plus x. Correct or not? What is y plus x in this picture? Huh? This part, Hey, what is this? What is this to this curve? Tangent. We call it a tangent cone. It's a tangent. Okay. It's not a coincidence. Let's try some more. Let's try some more. Let's say x equals to z of y squared minus x squared minus x cubed. This one we have keep using it already. The Norder qubit here. This is this guy here. Last time we blow this curve up. What's the C0 here? Z of y squared minus x squared. But what's this? This is actually the union of two lines. Z of y minus x, y plus x. This is the two crossing. Yeah. Again, it's a tangent line. Okay. See another one. Okay, another one. This one is more interesting, I guess. Z of y squared minus x cubed. Okay, how you draw this? Well, one way you can see this, you can use parametrization. And what kind of parameterization work? What kind of parameterization work for this curve? What kind of parameterization work? You can view it as a image of some map. I think last time we also see this kind of example before. What do you put? T cubed, T squared, the other way around, T squared, T cubed. Okay, from this, I think you could see better what's the image. You see, x part is always T squared, so it's always positive. So you only stay at the positive part. But y part, it follows the cubic shape. Okay, so it should be something like this. Okay, only positive part and then cubic shape. Okay, so what is C0 here? What should the initial one? Z of y squared. What is Z of y squared? Y equals to x axis. What's the difference of y squared and y? Also both y axis, right? But here got the multiplicity 2 here. What does it mean here? It means that this singularity has a multiplicity 2. I haven't defined for you, but somehow it tells you that a bit stronger than y equals 0. This line. So in algebraic geometry, right? Somebody they will draw it like this. They will draw a bit thicker here. It's a slightly different y equals 0 line. They draw it thicker. Yeah, no? Okay, although the tangent line is also horizontal, but they draw it thicker. This is one of the motivation that people study Hilbert schemes. They put all these multiplications together in the study. Try to parameterize these singularity. Okay. Okay, so far. Yeah. Okay. Right. So what's the real relation to tangent space then? Now I gonna show you another definition of tangent space, then we can discuss what's the equivalent, what is equivalent to what we have done before. So for f in polynomial ring of kx1 to kxn again, we will let f1 be the homogeneous part of degree 1. Okay, and then we'll define an ideal generated by this guy. We call it an ideal. We'll put F1, sorry, I1 to be the ideal, not ideal, or it's just set of F1 here. Okay, don't want ideal here? Let's keep it in this way. I'm not sure if we want ideal or not, but at least we have F1 here. Okay. Okay, and then again we have x and 0. Then what we will define another tangent space of x at 0 is t0x, okay, such that t0x equals to z of ix1. Is this equivalent definition to what we have did before? What have we done before? We take partial derivative, evaluate at a point, and then multiply by some degree 1 polynomial. Right, some degree 1 polynomial also. Yeah, but the way they get this degree 1, right, is how to get it. They look at the ideal that defines this x. Look at the first, the degree 1 homogeneous part, and then look at the 0. Is it the same thing or not? Is it the same thing? Maybe you'll try some example to get the idea. Okay. If I don't prove it to you, I'll prove it in the tutorials or in the notes. So let's give some idea what this tangent space is doing. Okay, let's say we look at the same curve again. Okay, look at the same curve here. And what is the tangent space at 0 in this case? Z of x plus y. Okay, the degree 1 part. Okay, the homogeneous degree 1 part. Then in this case, what can we tell about this point O? This point O is smooth or not smooth? Have we defined smoothness here? Let's see. Not smooth. Smooth or not smooth? Let's see. Huh? Smooth or not smooth? Huh? This one is a hypersurface also, eh? This one dimension of a hypersurface, eh? These two dimensions is the same, eh? Huh? Dimension of tangent space equals to dimension of variety, meaning what? That point is smooth. Singular means what? Maybe you have a larger dimension. Yeah, but these two are both hypersurface there. So these two dimensions should be the same. So actually, O is a smooth point. Okay, but we can look at another case. So let's say we look at Z of the nodal points again. Any degree 0 part here? Any degree 0 part? No, right? So your tangent space at x is z of 0. 0, 0 is what? Everything. The whole space. Okay. So in this case here, dimension of A2 and dimension of hypersurface same amount. Dimension of x is what? 2 minus 2, right? xy. 2 minus 1. So which is 1. But dimension of A2 is 2. Okay. So it's not the same. So all is not smooth. Okay. Similarly for 3. Just now we have the Caspiter case. Also don't have degree 1 term. Okay. So it's singular. Since T of x is the whole space. Okay. Yeah. Yeah. Try to talk about here. Yeah. So can you think about how we deduce tangent space previously? We take partial derivative with respect to y and x. Okay, and then we multiply these coefficients by y and x as well. Okay, so what can you observe here? You see, these are all degree greater than 1. If you do partial derivative with respect to x and y, you should keep at least degree greater than 1 variable x and 1. So if you evaluate at 0, you also get 0 0.1. So at 0, this homogeneous degree 1 part is the one that won't vanish. Remember, because if you differentiate it, you get 1. 1 evaluate at 0, you get 1. So they survive. But this 1 exactly you multiply to the variable xy. So it's the same variable that survives. So can you see the connection between these two definitions? Can you see the connection between these two? So actually how the partial derivative survive at 0? Exactly because your derivative is constant there. Okay, so I mean it's non-zero. I mean, yeah, it's non-zero constant. Okay. If you have higher degree terms, you differentiate, you put 0 in, then you get 0. Okay. The constant term inside this function here doesn't matter, right? Because you differentiate, you disappear already also. Okay, so it doesn't matter. So what's really matter really is the homogeneous degree 1. Okay, no? Those are the things that doesn't disappear when you differentiate. For sure doesn't disappear, right? It cannot be 0. The constant you get cannot be 0. Because x and y to stay, right, the coefficient cannot be 0. Okay. For x and y to stay, the coefficient cannot be 0. Okay, so yeah, I think I will write down a more precise statement on that. But there's one remark that I would like to tell you. Okay, which is the relation between tangent space and the tangent cone that we make just now. What's the relation between them? So one of them we use ix1 to build it. The other one we use ix in to build it. What's the relation between ix1 and ix in here? Ix1 is the one that I keep the homogeneous degree 1 part. Ix in the first such that the term is non-zero. The first degree such that the term is non-zero. Okay. So what? So if Ix1 exists, it should be part of Is in also. If it exists. Correct or not? Why is it part of? How you understand? Okay, that's one reason, but more doesn't mean that you have to be inside there, right? Why it could be the case that Ix1 is in Ix in. No, I mean like you need to argue why if you are in Ix1, then you are in Ix in, right? Huh? Wait, let me see. The Ix in, no, does it consider constant? Let me check. Huh? Oh, let me see. Okay, good. Very good. Okay, so since 0 is in my affine variety, I cannot have constant term here. So if Ix1 exists, that's the smallest one that could be non-zero. So that term must live inside Ix in. Maybe some of the F, the initial part could be larger, but who cares? Okay. So in this case here, if you apply Z to both of them, what you see is CPX is actually living inside TPX. Okay, so the tangent corner is living inside the tangent space. Okay, but just now what we see is like equal, right? It seems like it gives us what we want already. Okay, so have we proved this? As a dimension of CPX equals to a dimension of X. Have we shown this? Dimension of CPX is C. I think we haven't shown this. Okay, let's take this as a black box first. Okay, we haven't shown this. So let's say if this is true, so let's box it. Then it follows that actually the dimension of TPX is greater or equals to dimension of P. So this will make sense why we take dimension of TPX as a minimum one. This will make sense because the dimension of TPX is always greater or equals to dimension of X. Okay. And then furthermore, you can show that TPX actually is irreducible. Why is it irreducible? You can show that actually it's isomorphic to some affine space. And then in this case, we will get that dimension of TPX is equal to the dimension of X if and only if CPX equals to TPX. Okay. So in particular, when the point is moved, okay, whenever the point is moved, then the tangent con is the same as the tangent space. Okay. Make sense? Okay. I'll try and filling the gap. No worries. But what I want to tell you is this tangent con is quite useful construction. Okay. So far, okay. Okay. Really stop here. 5:40. 10. Okay. So I think we will clean out the last bit of blow up. So the picture you should remember is we blow up A2 last time, right? So the A2 blow out the surface at the origin, and all the line get lined up in the blow up surface. And then next up, we wanna do blow up on an AN. Okay, not A2 anymore, AN. But AN we will pair with PN minus 1. Okay, previously it's A2 with P1. Okay, now we'll do AN with PN minus 1. Okay. And then similarly, we can blow up the variety inside AN. Like last time, the one we do, right? We have a curve and then we blow it up. Okay, and then we see that, what we compute at the intersection is actually the tangent line. So we will use the tangent con idea here to speak about that in general case. Okay, and then we'll move on to PN. Okay, PN case, how to blow up PN. Okay, also PN with PN minus 1. So how to blow out a projective space. And then I think blow out will end there. I think at most we'll do it for one lecture, then we'll move on to device. Okay, please hope that I can finish my lecture not before next week. Huh? Okay, I got 4 assignments I have market. Huh? No, I mean I just finished the exam, so I will update you about it. Yeah. I just finished the exam writing spend, I think, longer time you answer the question. I need to type. It's so hard for me to type. I think I type like 1 day for the exam. Huh? You can type for me. Huh? Okay. Okay. So see you next week.